All right, let's get after Webwork 3. So, a radian, well, yeah, screw it. I'll tell you what a radian is. A radian is a distance, it's a length. And if you have a unit circle, so anytime you hear the word unit, you should think 1. So this is a circle of radius 1. Whoop, okay. So the distance, if you were to walk along this circle and go all the way around, right back to where you were, then the circumference of that circle is 2 pi. In general, it's 2 pi times the radius, but since our radius is 1, that's just the number 1. Okay, so now 2 pi being all the way around the circle, a fraction of 2 pi, like say we walk halfway around the circle. I walk halfway of that distance. I'm standing here. Okay, we can talk about I walked 180 degrees or pi radians. And if you work this out, you get pi. And so you can either remember that 2 pi is 360, or you can remember that pi is 180. Sorry, there's degrees over here. And it's a way to go between a length, technically radian is unitless, I think, I don't know, whatever. A length and a degree measurement of how far around you walked. And this is going to serve as our conversion factor. So 26 degrees is equal to 26 degrees times 1. Yeah, that's true. Oh, but you know what I want to do for the number 1? I want to write the number 1 as pi divided by 180. Okay, technically 180 degrees. And now this is how you would convert the degree measurement into the radian measurement. And I don't think it's too nice. What's 26? 26 is 13 and 2, and 13 is a gross prime number, so this is not going to reduce very nice. It's 13 pi over 90, and that's about as far as we can get. So if I entered that in here, then it would say it's correct. I don't really want to mess with it, but yeah, okay, for the sake of the video, we got 13 pi divided by 90. And let's submit, and there it is. Okay, what's the decimal approximation of the radian measure? So does this, hey, look at that. See how it's entered and it says 0.453786, blah, blah, blah. Well, it doesn't say how many decimals to enter. Oh, no, it does. 3 decimal places. Oh, thank goodness. Okay, does that mean truncate or round? I don't know. Let's find out. I'm going to round it really quick and see what happens. It might yell at me. No, it's okay. So I could round or truncate. The 7 could make the 3 and 2 a 4. Sorry, I don't know how to make my cursor highlight, so I can just say, look at the entered column. All right, let's go to the next problem. Same idea, and now we're converting the pi stuff to the degree stuff. So I have pi over 3. Now, you could ask yourself, look, 2 pi is going all the way around the circle. What would I have to multiply this by to get pi over 3? And if you think about it, well, 1/2 would kill the 2, and if you introduce a 3 on bottom, you get a 3, so that's 1/6. We're walking 1/6 of the way around the circle, and sort of this is what we're looking for. This is conceptually what's happening. It doesn't actually answer the problem, right? The problem wants the degree measurement. So I'm going to use this conversion again, and I have pi over 3 is equal to pi over 3 times 1. Okay, yeah, we've been here before. The way I want to dress up the number 1 is like this, 180 degrees divided by pi. And now the pi's cancel, and it's 180 over 3, or 60 degrees. And yeah, if you walk 1/6 of the way around the circle, then you really have 360 divided by 6. And again, you'll get back to 60 degrees. So, all right, here we are, 6-0, submit, next problem. Boop. Okay, so now we want to get used to, how is that possible? Oh, well. All right, we want to get used to just the general sense of what's positive and what's negative. Okay, we don't really need to know the unit circle too thoroughly. What a fantastic circle. If I just hold, then it'll snap too. Great, we'll do that. Sweet. And then I'll ruin it with this. No. All right, so this is 90 degrees. It's also 1/4 of the way around the whole circle. Okay, whole circle is 2 pi. Whoop. It's 360 degrees, whatever. So work this out, you get pi over 2. Okay. So some of the fractions, such as 2 pi over 13 in the third spot, right? All right, how comfortable do we need to be with fractions? Well, you don't need to be comfortable at all. You could always convert back to degrees and use the 90-degree reference. But, all right, look, I mean, the way my brain thinks of this, and if no one's ever told you this, it might be a useful insight, is to think of it as 2/3 of a pie. Okay, so what the heck does that mean? Sorry, not 2/3, 2/13. My apologies. It doesn't matter what it means. What matters is that you can look at this number and know that if you only have 2/13 of something, you definitely have less than half. But you definitely have more than 0, okay? And if you can figure that out, then you know you're in this range here. Okay, so greats are all these sines. No, we got some sines and some cosines. All right, so I'm going to press pause on this type of talk, and let's talk a little bit more about the unit circle here. All right, again, unit circle means it has radius 1. This is 1, 0. Okay, now, there's a lot of stuff that goes in circles in life, and you could imagine that it'd be useful to describe position on, like, say, two-dimensional thing in terms of x and y coordinates. That could be very useful. And at the same time, if my entire existence is stuck to living on this circle, then if I know how far around I've gone, then if you think about it a bit, you could be like, well, wait a second, wouldn't that tell me my x and y position? Shouldn't x be a function of theta? And shouldn't y be a function of theta? And so from knowing this information, I can get this information. And it's true. And some people sit down and crank it out, and then those functions got so famous, they got names, and their names are cosine and sine. I don't have great mnemonics for this, but it is in alphabetical order. X comes before y, and I want this one, right, nice. And, sorry, yeah, X comes before Y and C comes before S alphabetically. So I don't know if that'll help. But all right, so we just need to describe the X coordinate and Y coordinate in terms of positive and negative. And in this first quadrant, they're both positive, right? My X is over here, my Y is over here. Both things are positive. In this next quadrant, my X is negative, but my Y is positive, right? Because I'm to the left, but I'm still up. And then here I have negative, negative. And then here I have positive, negative. Okay? So if we just have that quadrant breakdown, then we can figure out all of these problems. All right, let's run through them. So 36 degrees, 36, famously less than 90. It's somewhere around there. So we're going to have a positive y value. So positive, because sine is the y value, right? All right, cosine of 3, just shy of 360, 359. So that means we went, ooh, almost, no touching. Okay, so what's happening? It looks like the x is positive, and that's what we care about. It's just the x value. I don't need to even look at the y value, right? Cosine is x. All right, now the 2/13 of a pi we talked about previously. It's somewhere around here, and so the y value is positive. Ooh, 11/15 of a pi. So 15/15 would be a whole pi, and 1 pi is 180 degrees, okay? So we don't quite have that much, but we definitely have more than half, right? Because 7.5/15 would be 1/2. So that means we've broken this barrier, and we keep going, and we stop somewhere in here, okay? All right, so that's a negative x value, and that's all that we care about. There we go. Next problem. Without using a calculator to find the exact value, all right, not a decimal approximation. So there are some famous values that we should talk about, and these do not get tested on very harshly. This is on a Webwork, but you should not really expect this type of knowledge on an exam. So, all right, with this unit circle, so if here's the center, and if I put down the x and y axis, then right off the bat, we should be able to figure out these 4 spots, because the word units in unit circle means radius 1. Okay, that looks like a 2. 1. So this is 1 step to the right and no steps up or down. This is no steps to the left or right, but 1 step up. This is a step to the left and no steps up or down, and then no steps left or right, but a step down. Okay, so those, I hope those make sense. Now, let's draw the line y equals x. This is the line y equals x, okay? And let's also remind ourselves what the equation of a unit circle is. It's y squared plus x squared is equal to 1. Okay, if you can remember this, then we can actually figure out everything else, okay? Now, if you're the type of person who just wants to memorize, then I'll tell you the answer first, and you can kind of skip ahead until you see me draw more on here, okay? So this is going to be 1 over the square root of 2, comma, 1 over the square root of 2. And if you were thinking, when I wrote this number, if you were thinking, gosh, what's this number going to be? Then I would encourage you to keep watching, because the point is, we knew the y value, it's the x value. There's usefulness here. There's usefulness in thinking about, what did we draw? What does it mean? Okay, now that being said, I did not describe how we knew we were dealing with 1 over square root of 2. So now let's jump into that description. And the whole idea is that on this red line, y is equal to x. So let's use this equation and let's substitute that in. Now it doesn't matter if you would like to substitute y for x or x for y. I'm going to substitute x for y. So in other words, the y squared, oh, that's gone now. Now it's an x squared because x is equal to y. And this has to equal 1. And famously, if you take something and add it to itself, like say a plus a or 1 plus 1, you get 2 copies of that thing. That's a times, okay? So this is 2 copies of x squared, and that's going to equal 1. So now I divide the 2 over, and now x is either the positive square root of 1/2, which is the same as 1 over root 2. You can take the square root of the top and the square root of the bottom. Or it's the negative square root of 1/2, which is negative 1 over root 2. And this is where we have to look at the point that I have labeled. This point in red has a positive x value, so I must be dealing with this one. But then you know what we get for free? Over here, this has a negative x value. I bet its x value is this one. In fact, it has to be. It has to be this guy. That's negative 1 over the square root of 2, drawn poorly. And what's the y value? Well, y is equal to x, so it's negative 1 over root 2. Okay, so I'm not even going to worry about radians or anything yet. I just sort of want to figure that out. And in fact, with this trick, by the way, you can figure out any sort of nice fraction-y ratio. So if instead, I'm going to erase everything I'm about to draw, but I'll still draw it nonetheless. This line, this is the line y equals mx, and I'm not going to specify what that is, okay? But y equals mx, you can, again, substitute into the equation x squared plus y squared is equal to 1. And if both of these are true, that happens at the intersection. We're talking about this spot here. And if y is equal to mx, I can substitute mx in for y. So, oops, sorry. I can substitute mx in for y, so this is mx squared. That goes there. And that needs to equal 1. And then you could solve for x. In fact, let's just do it really quick. So what is this left-hand side? It's x squared plus m squared x squared. And if I factor out the x squared, which is actually the same thing I did down here, you could think of this as factoring out the x squared, and then I have 1 plus 1, and that's where I get the 2 from, okay? But in general, it's going to look like, all right, let's look at this left-hand side. Let's look at this right-hand side. I'm going to copy and paste everything up here for a moment. So if I factor out the x squared, then on the left-hand side, I have 1 plus m squared. And on the right-hand side, I have 1. And now we can solve for x. It's going to be, I'm going to write it like this, actually, 1 over the square root of 1 plus m squared, okay? I divided this over, and then I took square root, okay? So now we know, given a slope, what this spot has to be, okay? So how can we connect this back to, how does this help me figure out, like if I have 4 pi over 3, right? And I want the sine value of that. All right, so now what can we do? Well, 4 pi over 3, okay, pi is 180 degrees. So this distance would be 1 pi, also known as 3 pi over 3. And then if I can go a third of the way back to the start, then that's covering another third of a pi. And so if you have 3 over 3 plus 1 over 3, you get 4 over 3. Okay. So anyway, this line here is a third of the way going from here to here. Okay. And we could figure out that slope potentially. What could we do? Well, whatever that's... Do I want to... Is this worth the time? I don't know. Here's what I'll say instead. We know this whole thing is 180 degrees, or pi, whichever you'd like, and we did a third of it. So that means that this segment here is a copy of pi over 3, or 60 degrees. Okay, however you like to think of it. So, oh, too big. All right. So, now, first off, if you have a calculator, you can just input this. In fact, you may have just skipped all this and just input a calculator. Great, cool. Make sure your calculator is in radians and not degrees. Now, what's happening is this is a 60 degree, or a pi over 3, that thing I just erased, and I decided to write again because now I'm going to hop down to, there are essentially 2 triangles to know, okay? If you don't want to have to use a calculator, or if you want an insurance policy in case you forget a calculator. So one triangle is called a 45, 45, 90. Okay, this triangle has ratios 1 over root 2, 1 over root 2, and 1, and these ratios scale. So if instead of this being the number 1, this was the number x, then this would be 1 over root 2 times x, and 1 over root 2 times x. Similarly, this is 1 times x, okay? So that's one of the famous triangles. The other famous triangle is a 30, 60, 90, which looks like this. Boom. And because I have grid paper, it's pretty easy to draw because, so this length here, well, look, this is length 1 and this is length 2, so this has to be the square root of 3. And if you're thinking, wait, how'd you get that? Pythagorean theorem, I have a squared plus b squared is equal to c squared. And, wait. What's going on? A squared plus b equals c squared, and wait, so then that would look like 1 over root 5. Oh, because I want a 1/2. No, this is, oh, I see. Shot myself in the foot, y'all. That's not the triangle we care about. I didn't draw it right. It is hard to draw, because actually the long leg is distance root 3, and I should have known. There should have been just red flags going off. You know, we all have silly brain moments, okay? So this is not drawn to scale because this length is bigger than 2. And we should have had some fire alarms going off in our head because when I did this and I said 2 and 1 and root 3, well, if we have some number sense, root 3, this is about 1.7, and you don't need to know that, but if you knew that's less than 2, and that's something that we might know without knowing we know, because 3, famously, less than 4. And if you take the square root, it's still true, and there's that, and there's that. So anyway, all right, so I should have caught that. I'm sorry. All right, here we are, this triangle, and I should actually draw it bigger so I have room to fill in some stuff. Great, we'll just go out like this and like that. Great. So the big leg, which has root 3, that's opposite the big angle, 60 degrees. The small leg, which is size 1, is opposite the small angle. And then there's a 90 degree, and that has length 2. And again, this scales, so if this was 2x, then this would be 1x, and this would be root 3x, okay? So this is called a 30, 60, 90, and this is called a 45, 45, 90. And in radian measure, it's weird because things seem bass-ackwards. So remember, so if you think of a number and you divide it by something small, then this thing as a whole is bigger, okay? So 2 divided by 0.1 is 20, right? It's bigger than whatever that number used to be, okay? So when I take the number pi and I divide it by 3, versus if I take the number pi and I divide it by 6, then this one is bigger because it has a smaller denominator, okay? And ooh, this is going to play tricks on our brain because 3 is smaller than 6. And I get it. It happens. Brains be thinking fast and trying to make jumps. You got to slow it down sometimes. Anyway, same triangle, but now it's with radian measure. And this is pi over 2. So pi over 3, that's what we're staring at right here. It's a pi over 3, whoop, which means this is the long leg, so it's a root 3, and this is the short leg, which is a 1, and now we have to scale, okay? So what do I mean by scale? As drawn, this has side length 2, but over here, this is a unit circle, so this has side length 1, all right? So in fact, 1, famously, 1/2 of 2, so I have to scale all these ratios by a factor of a half, okay? 1/2 is how much I have scaled 2 here. So like here, when I have this x, 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 I'm plugging in x as a half, okay? That way I can get a 1, and I can get a 1/2, and I can get a root 3 over 2, okay? All right, so anyway, what this is looking for, flip this around, put that away, click here again. We have minus the square root of 3 divided by 2. Sorry, I already spent long enough on that problem, and at the end of the day, you're allowed to use a calculator, so none of this matters. Burn it all down. Okay, great. Dun, 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 dun. Sweet. All right, so now there's a formula that we need to remember. So let's just write this down, okay? So this is for sine and cosine. The formula we're going to use over and over again in this class is you have amplitude, and then I'm going to do sine first, sine, and then 2 pi over t, and t is called the period. And maybe a decent mnemonic is that periods measure time, and that's why we use t. All right, and then we have x minus phi. Phi is called the phase, and plus, and this is where it sucks because a is already used, so I'm going to say AV, and this is the average, okay? Average, whatever. Okay, so let's make sense of this. Let's take a peek here, and can I just copy this? That'd be nice. Copy image, and paste it here, maybe. Oh, nice. Okay, great. So, let's get a lighter color. That might be too light. Let's see. Yeah, I don't like it. All right, so here's 1, and here's, if that's a 6, this better be a 5. Let's check. 2, 3, 4, 5. Yes, that seems good. Okay, what's the average between the lowest and the highest? Well, 1 plus 5 over 2, that's 6 over 2, that's 3. And yes, we can also just sort of visually see if you cut this in half, there's my average. It's 3. That's what's going to go here, okay? Now, look, they're not asking for a formula in this case. They're only asking for certain things. Let me go to the next problem really quick and see how it says f of x equals. You're going to need to know this formula. So I'm going over it now, and then we'll fill in the blank. All right. Sweet. All right, what's the amplitude? Let's change our color for that. Amplitude is referring to the distance between the average and the peak. And it doesn't matter, that's the same distance as between the average and the valley, okay? And we can sort of see, well, going from 3 to 5, or going from 3 to 1, that's a distance of 2. It doesn't really matter, right? So, okay, that's a distance of 2, and so that's a 2. So far, we have 2 sine, and then it's going to be 2 pi over, and we have to figure that out, x minus, and we have to figure that out, plus, and then we have a 3. 3. Great. All right, let's figure out these missing pieces. So now we need a period, okay? A period. And that is the distance from peak to peak. All right, that's sort of the easiest way to find it. And it's a little chopped off in here, so can we see it here? Maybe if I zoom it. No, that's disgusting. That's very cruel. I'm guessing that this truncated number here is supposed to be 1. That's my guess, okay? So peak to peak is the same as the distance from valley to valley, okay? So if I go from 0 to 1, assuming that's what that is, then my period is 1. It's just that distance, okay? So small thing, get this out of the way. My period is 1. All right. Here's one of the most subtle things, but we'll be fine, okay? The phase, phi, the phase. So when you're dealing with sine, you need to, if you are walking along the average, okay, so I'm walking along the average, find the spot where you go uphill. Right here. Right here I go uphill. If you're walking along the average here, it'd be right here, right? Sort of, how do I say this? I'm walking along the average, and when I hit my graph, I have to walk along my graph. Boop, I'm going uphill, okay? Boop, I'm going uphill. All right. So now we need to figure out this distance, and that's called the phase. And notice they do not ask for it in this problem, right? To me, it looks like the phase is about a third, okay? I can probably fit about 3 of those in there, but it doesn't matter. They don't ask for it here. But this would be the equation form of this function, okay? And the phase you use has to do with the trig function you choose. So we'll see that on the next problem. For now, let's go ahead and enter some stuff, okay? So the amplitude was 2. That's the distance from the peak to the average. The maximum value was 5. The minimum value was 1, and I think the period was 1. It's very hard to read on that graph. Great, we're good to go. All right, let's play this game again. And notice how they give us more numbers this time, and things are a lot more clear. Great. All right. So, in fact, it looks like they sort of clearly mark the average for us. And that is... Oh, nope. They don't clearly mark the average for us. Okay. So we have a minimum. I should use the same colors. All right. So my amplitude is going to be the distance to the average. So we should figure out the average. And actually, that black line looks a little bit lower than what the average would be. I think this is the average here. Okay. And we can figure it out by just adding the min and the max and dividing by 2. So 6 plus negative 4 is 2 over 2. We get 1. Okay? So my average is 1, which means this formula is going to end with plus 1. All right. And hey, this is kind of nice because if I'm walking along the average, I go uphill. It looks like it's supposed to be 0. So phi is equal to 0, okay? And, all right, stupid mnemonic, but to remember walking along the average, you're walking along and singing phi, fi, fo, fum. Where do I go uphill? Okay, so, I regret nothing. Okay, let's figure out the amplitude now. It's the distance from the average to the peak, or the average to the valley. So what's the distance from 1 to 6? It's 5. And I didn't give myself enough room here. Stop it. Great. That should be good enough. Let's get a small one. It's already small. Great. All right, so I'm going to use sine. And because I'm using sine, that's connected to the fact that the phi that I use is when I'm going uphill. Okay? All right. And so this is going to be x minus... And in this case, it was 0, but yeah. All right, now I have 2 pi divided by, and now we need to figure out the period. And so the period, I previously said valley to valley or peak to peak. You just need to find a spot on the curve that repeats. And that's, peaks and valleys are nice. Because, for example, so this is not the correct answer, what I'm about to write. You might look at this and look at that and think, oh, that's a spot that repeated, but it's actually not. So if you were walking along your curve, let's get another color. Now let's go back to green if we're walking along my curve. Okay. Right here, if I'm on my curve, so I'm not on I'm on this blue curve here. Okay. Then I'm going downhill, right? I'm going downhill and I'm touching that pink average line. And I walk and walk and walk and walk and walk. And then when I'm standing here, I'm going uphill and I touch that pink average line. So even though I'm at the same y value, I'm not at the same spot along my curve. And I walk and walk and walk and walk and walk. And now, haha, I'm touching the pink line and I'm going downhill. That is the same spot. Okay? So this distance is the same as this distance. Okay? And it's easier to see in the top form because I have the numbers 2 and negative 2. So the distance between those two is 4. All right. I've officially ruined my color coding, but okay, 4 was the period. So here's a potential formula. Let's go ahead and enter it. I have 5 sine of 2 pi divided by 4. And you could write x minus 0, okay, but x minus 0 is the same as x, so I'm just going to write x and then plus 1. And submit. Great, there it is. All right, so that's one of the forms that we need to know. Let's see if they ever force us to use cosine. They don't force us, but this is an example of where cosine is sort of easier to see the face. So, all right. Boop. All right, let me give you a mnemonic for how these things look. So sine, if I knock that letter over, okay, then it would look like this, right? That's how a sine curve looks, where it sort of starts right there, okay? So the center of the letter becomes the center of where you knock it over, okay? Now cosine, center of the letter, let's knock it over, whoop, okay? Begins looking like that. The actual cosine graph has to sort of do some other stuff. It probably actually technically ends right there, and then have to come, wait, hold on. Right. Who cares? All I care about is where it starts, okay? So, it starts and it looks like this, right? Okay, so the formula for cosine, it's still blank, cosine 2 pi over blank, x minus blank plus blank. All right, everything except for phi stays the same, okay? So, phi is going to be we'll deal with it in this graph, actually. So that way, words are just easier to learn with examples, right? Paste. Great. All right, here's our handy-dandy y-axis, and right here is a peak. This distance is phi for cosine. So it's, right, cosine starts and it looks like this if it's not moved around. And so phi is telling you, hey, it used to look like that, but you moved it over here, okay? So that's what's happening. Cool, and then we can very clearly read that off. It's 8, right? Okay, so there's an 8 here. Let's do something else. Here, the average, I think it just looks like 4, and I'm just going to run with it, okay? And if the average is 4, then that means we're going from 4 to 0. The amplitude is also 4, okay? And now we need a period, so I need to find where this wave repeats. So you could use valley and valley, right? And that looks like it's a distance of 16. So this is going to be 2 pi divided by 16, okay? I'll show you how to do sine for this same graph next, but let's enter this really quick. Cosine of, and then 2 pi over 16, and then we have x minus 8, blop, blop, plus 4, and let's see if it likes it. Submit, and it does. Great. Okay, let's run through this with sine. Okay. Boop. All right, so for sine, all these values stay the same except for phi, right? So it's still an amplitude of 4. It's still going to be a period of 16, x minus, we need to figure that out, plus, and then 4. Now, if you write sine and you write 8, you're going to get it wrong. Let me show you. Here, 1, 2, 4 sine, okay? And submit. No good, right? And that's because the 8 was telling us how far we moved the starting point of the cosine graph. And so analogously, we should ask ourselves, how far do we move the starting point of the sine graph? Okay, well, how can we figure out the starting point? There's only one subtlety here, and the subtlety is you're walking uphill, okay? I'm going uphill. Because a point that looks like this is going to happen over here and over here, but over here, you're walking downhill. And over here, you're also walking downhill. We always want to travel from left to right, okay? So I go over here, and this is the wrong spot. This is the good spot. this spot, I'm on the average, right? The average is 4, and I'm walking uphill. And so I'm curious about this distance here, and we can see that it's 4, okay? It's the distance from where that spot used to be, which was exactly x equals 0, to where that spot is now, which is going to be x equals 4, right? The graph used to look like this, and it got shifted over by 4. So let's go over here. Here, we'll delete 4, and now let's hit submit, and now it's correct. Okay. All right, next problem. Sweet. So now we get into the stuff that I actually like. Memorizing sines and cosines, I hate it. All right, so consider the discrete time dynamical system, which we're going to forever abbreviate as DTDS, given by the number of bacteria next year, minutes? What are we looking at? How do we measure this? This is a yearly volume. There's a word year down here on the bottom right. Okay, so the number of bacteria next year is twice the number of bacteria this year. That's what this is saying. All right, and each bacteria takes up 10,000 micrometers cubed. Write an updating function for volume. Well, so 1 bacteria is equal to 10 to the 4th micrometers cubed, okay? And we have B sub t number of bacteria at time t. That's what this represents. That's why we use these two letters. B is letting us know we're measuring the number of bacteria, and T lets us know when we took the measurement. But as a whole, B sub T is a population. And each member of that population has this much volume. So, in fact, the volume next year is the volume this year times 2, because the volume just scales directly with the population. Like, the fact that the population doubles is why the volume will double. If you have 1 bacteria, I was trying to give that depth, whatever, and it has whatever, that volume, and it doubles next year, well, your volume doubled. So this is a 2, and this is a 0. Submit. Great. Now, some of you are going to have more interesting problems. In general, well, let's see what my next one looks like. Maybe it'll be more interesting. Yeah, great. So if your previous problem, if I didn't answer it, then watch this one and go back. Okay? So let's, order matters. Order matters. Okay? What do I mean by that? So population of bacteria triples every hour, but 4 million bacteria are removed after reproduction. All right, so I start with some amount. So I start with the amount at time 0. An hour goes by, and they tripled. Sweet. And then that instant, right after they tripled, so after reproduction, I remove 4 million. Okay? So this is remove after. Okay? Words matter. Order matters, and words matter. Okay? If yours says that's removed before, okay, well, that means I had some amount of bacteria, I removed 4 million, and the remaining amount is what triples. And notice how that changes things. Bop, bop. This is like a 3b0 minus 12, and that's going to be the amount of bacteria the next hour versus here's the amount of bacteria the next hour. Okay? And there's nothing special about my initial amount. This is really just however much there is, it triples, and then I remove 4 million, and that's how much there's going to be. Versus however much there is, I remove 4 million, that result triples, and that's how much there's going to be. Oops, plus 1. Okay, sweet. So let's make this, according to mine, it's just that. Oh, nope, sorry, plus -4, because I'm removing bacteria. You can imagine if you add bacteria, so if you add, then this would be a plus. And if you add be 4, then this would be a plus, right? Okay, next problem. All right, so this is just making sure we can use an updating function. An updating function is that equation on the first line that says L sub t plus 1 is equal to L sub t minus 1.7. So the fact that L0 is 13.1, well, look, that's a t equals 0, and if I plug that in, then the result is going to be L sub 0 plus 1, better known as 1. So to get L1, which is what this is asking for, I need to do L0 minus 1.7. So L0 minus 1.7. Okay. Great. Now to get L2, I have to do L1 minus 1.7. L1 minus 1.7. And to get L3, I have to do L2 minus 1.7. And notice what's happening. The number of times I subtract 1.7 is the same as the subscript. So look, you might feel more safe if I wrote that, but it's the same thing because of order of operations. You are forced to do the multiplication first. So alternatively, I could have written, this, it just doesn't matter. But L5 is going to be the initial amount minus 5 copies of 1.7, just like how L3 right here was the initial amount minus 3 copies of 1.7. And here I'm just going to just goof around. So there's a total of 4 copies of 1.7. And in general, it's t copies of 1.7. And so now if I take this and I put it here and make that t a 20, we're good to go. Submit. There it is. Boom. All right, next problem. All right, the next b value, b subscript t plus 1, is the current b value times 2.5. b subscript t plus 1 is the current b value times 2.5. Sweet. So b1, that's the next one after b0. So I should take b0 and multiply it by 2.5. So 2.5 times b0, which is 8. That's what this is saying. All right. You know what? I actually want to write it the other way just to make, how last time I tried to make the pattern clear by copy and pasting. I'm trying to do that same thing here. Okay. So what's b2? Well, it's the previous population times 2.5. Dope. What's b3? It's the previous population. I need to catch up. There's the previous population times 2.5. So what's happening? Well, there's this many copies of 2.5. When it was b3, there were 3 copies. When it was b2, there were 2 copies. When it was b1, there was 1 copy. And when it was b0, there were 0 copies. All right. So now use the solution function to compute it. Well, it's the same as what we've already been doing, but now I'll just write it like this. I'm being a little lazy. There we go. Great. Do you agree with your iterations? Do your answers? Yes, they do. Do I have to type all of yes? We'll see. Great. So there you go. All right. All right. Now I need to come up with an updating function. So we're curious. We have this table here, t, h sub t, h sub t plus 1. And I want to know, how do I get from h sub t to h sub t plus 1? So how do I turn a 5 into a 6? Is it the same way you turn a 6 into a 7? Is it the same way you turn a 7 into an 8? Is it the same way you turn an 8 into a 9? Hell yeah, it is, man. I take what's there. So I take 1 copy of what's there, and I add the number 1. Okay? All right. Now, for this blank, the h of t, it's silly, okay? And what I mean by it, the word it is doing strong lifting. H of t and h sub t are the same thing, okay? It's just a matter of whether or not we felt like writing parentheses or we felt like writing a subscript. But the whatever h is measuring, maybe it's the height of something, it's a function of time. And so the reason for this subscript is it's letting you know, hey, the height is a function of time. And the same reason that we have these parentheses, it's saying, hey, the height is a function of time. Okay? So this blank, the one I'm working on, this guy, is asking, what is that function? How do I get from this column to that column? Okay? How do I turn a 0 into a 5? Is it the same way you turn a 1 into a 6? Is it the same way you turn a 2 into a 7? Hell yeah, it is, man! I'm adding 5. So I have t plus 5, right? T is referencing the number in this column, and I add 5 to get the number in that column. Boop. All right, cool. That's it. See you next time.